Hello, welcome to ATI 4640. Last session we addressed the network of partners who will work together to process the raw material and deliver that to the end user. The network of partners was called the supply chain. A very important part of the supply chain was the logistics system. The and those are the different activities required to move the material, information, and transactions within the supply chain. Part of that system and part of the supply chain is having the received material waiting in a warehouse until being processed, and the processed completed products stored until shipped. The stored material are called inventory, and the activities of receiving, putting away, moving, retrieving, processing, packaging, and shipping need to be managed through what's called an inventory management system. Inventory management will be the topic of this session. One of the most interesting stories about inventory management is Amazon.com, which started as a virtual retailer. No inventory, no warehouses, no overhead, just computers taking orders to be fulfilled by others. So basically, when you buy something, another person will be selling that for you, not a company, or could be another company. So basically connecting the seller with the buyer. Over the past 14 years, and due to the growth of Amazon.com, the company was forced to become the world's largest or leader in warehousing and inventory management. To manage all orders efficiently, each order is assigned by computer to the closest distribution center that has the product or products. A flow master, which is in German word for master. So master is master. So basically, as if we are saying that the flow master, which is somebody or who's somebody who has the experience to coordinate and assign the work to the teams responsible for getting that order ready for shipment. Robots and technologies help workers move merchandise and pick up the correct item. If you click on the word robot here, I added for you a link. You will see a video clip demonstrating robots moving products in the warehouse at Amazon.com. Once selected, products will be placed into crates on a conveyor. Barcode scanners scan each item 15 times to virtually eliminate errors and make sure that we are selecting the proper item to be shipped to the end user. Crates arrived at central point where items are boxed and labeled with a new barcode. Gift wrapping is done by hand at 30 packages per hour. Completed boxes are packed, taped, weighed, and labeled before leaving warehouse in a truck with the latest delivery fleet deployed by Amazon and the Prime services. Orders can arrive at customer within 1 to 2 days, and that's with the Prime account, free shipping 1 to 2 days. So to understand the objective of inventory management, let's define inventory first. Inventory is the raw material, components, parts, or work in process or finished even products that are held at a location in the supply chain. Inventory management is the supervision of non-capitalized assets and stock items. Inventory management supervises the flow of goods from manufacturers to warehouses to distribution center and from facilities to point of sale. The objective of inventory management is to achieve satisfactory levels of customer service while keeping inventory costs within reasonable bounds. Inventory is one of the biggest corporate assets representing as much as 50% of total invested capital. Investment in inventory is currently over 1.25 trillion based on the US Department of Commerce, which accounts for almost 25% of the GMB for the United States. Controlling inventories could lead to increased corporate efficiency. Right inventory at the right place could lead to growth in sales, cost reduction, and meeting customer demands. The function of inventory is to provide a selection of goods for anticipated demand and to separate the firm from fluctuations in demand. It can also function as a assembly facility to decouple items or to deassemble items. So you can make it for assembly, you can make it even to deassemble parts and to resend it to different places. Inventory will assist in taking advantage of quantity discounts and protection against inflation. I will talk about the mass ordering or the volume ordering for these companies, which will assist on protecting the companies against any changes that might happen during the year. Inventory has different types based on the material and the different functions assigned to their inventory. Inventory could store raw material, which is a material that is purchased but not processed. Could include material that undergone some change, some type of processing but not completed, which is called work in process material or inventory. The company could have the maintenance, repair, or operating parts or components that are necessary to repair machines and to keep machinery and processes productive. In addition, inventory could hold finished goods or completed product awaiting to be shipped. This figure shows the material flow cycle. 95% of the flow time, the material will be waiting for inspection to be processed, waiting to, until the machine is reconfigured, waiting until being shipped. So most of the time it's waiting. Processing the material will take only 5% of the total flow time. So to understand inventory management, we need to examine how inventory items can be classified using ABC analysis. And we need to examine how accurate inventory records can be maintained. The ABC analysis divides inventory into three classes based on annual dollar volume, where Class A has the high annual dollar volume. And we'll talk about what each one of them means and how it works in details later on. Class B is the medium annual dollar volume, and Class C is the low annual dollar volume. This approach is used to establish policies that focus on the few critical parts and not the many trivial ones. Although Class A items may represent 15% of the total inventory, but they will have the highest percentage of usage, which might reach up to 80%, or of sales, which have the highest annual dollar usage amount. Class B items may represent 30% of inventory items, but 15 to 25% of the total annual dollar usage volume. Class C items may represent 55% of total inventory items, but 5% of the total annual dollar usage volume. This slide shows an example of a company called Silicon Chips Incorporated, who manufactures some super fast DRAM chips. The company would like to categorize its 10 major inventory items using ABC analysis. The table in this slide shows the 10 items identified by the stock number, their annual demand, and unit cost. The first two items have the highest percentage of annual dollar volume with 72% and can be classified as A items. You can see that most of sales are for the first two items. And again, although the percentage of number of items in stock is 20%, but the annual dollar, the most sale for them is 90,000 for the first, $77,000 for the second, and again they represent 72% of most sales. That's why we call them class A. The percentage of the annual dollar volume can be found by dividing the annual dollar volume by the total dollar amount. For example, 90,000 for the first item divided by the 232,057, which equal to 38.8% for the first item. The third, fourth, and fifth items represent 23% of the annual dollar volume and can be classified as B items. And all the rest of the items represent 5% and can be classified as C items. So we have now A items, B items, and C items. There are other criteria than the annual dollar volume that can be used in the ABC analysis to decide of the item or if the item should move quickly from the inventory. Should we don't keep it on shelf or move it as quickly as possible from inventory. Those factors are the high storage cost or holding costs. As long as it stays on the shelf, it costs us a lot of money. So I need to move it or sell it as soon as possible. The anticipated engineering changes that might happen. Maybe that product will be obsolete, so I need to move it as soon as possible. The delivery problems, the quality problems that will be associated with it. So all these factors also will assist in the ABC analysis and to decide which one is class A, which one class B, which one class C. The advantages of dividing inventory items into classes allows policies and controls to be established for each class. Policies that may be based on ABC analysis include more emphasis on supplier development for A items, tighter physical inventory control for A items should be placed in a more secured area, or the accuracy of the record should be verified more frequently, and more care in forecasting A items because they are the most important, so I need to forecast them accurately and more frequent. Record accuracy is very important for production and inventory control. To make sure of the record accuracy, a periodic check of inventory should be conducted. An automated or semi-automated process can be put in place to track receipts and subtraction on a continuing basis of what's being shipped or what left inventory. Accurate records are critical ingredients in production and inventory systems. It allows organizations in general to focus on what is needed. It's necessary to make precise decisions about ordering, scheduling, and shipping. Incoming and outgoing record keeping must be accurate. Stock rooms should be secured. Cycle counting is a periodic system and physical count of items made at periodic intervals. Perpetual or continuous inventory system, a system that keeps track of removals from inventory continuously, thus monitoring current levels of each item. It's often used with ABC analysis. And we have the cycle counting that has several advantages, such as it eliminates shutdowns and interruptions. It eliminates annual inventory adjustment. It has trained personnel audit inventory accuracy. It allows causes of errors to be identified and corrected, and it maintains accurate inventory records. The example in this slide addresses cycle counting. Coles Trucks Incorporated, a builder of high quality trucks, has about 5,000 items in inventory. An operations manager student assisted the company to classify their items using ABC analysis, where they found the following: 500 A items, 1750 B items, and 2750 or 2750 C items. The company's policy is to count A items every month, 20 working days. The month is 20 working days because in each week we have 5 days, so we consider that the month is 4 weeks. 5 times 4 is 20 working days. B items every quarter, that means every 60 days, and C items every 6 months, that means every 120 days. So how many items should be counted every day from each item, and what will be the total? Based on the provided policy and the number of items in each classification, Class A item will be counted 25 items per day, while B will be counted 29 items per day, and C will be counted 23 items per day. That is a total of 77 items that need to be scanned or counted on a daily basis. We might think that service sector does not have inventory, but intensive inventory is held in wholesale and retail businesses, making inventory management a critical component of profitability. In food services, controlling inventory is often the difference between success and failure. In addition, inventory that is transit or idle in a warehouse and inventory damaged or stolen is a loss. Inventory that is unaccounted for between receipt and time of sale is known as shrinkage, which occurs from damage or theft. Shrinkage can also occur as a result of sloppy paperwork that was not done accurately. To minimize loss, we can use techniques such as good personnel selection, selecting the proper people that can do the job, even doing more training for them so they will know how to do it correctly, and discipline. We can also have tight control of incoming shipments, and we can have effective control of all goods leaving facility. We will have a tracking system that knows or that can track every item that leaves the facility. This slide compares the independent and dependent inventory models. So we have different models, different approaches to look at the inventory. The main two is the independent demand and the dependent demand. Independent demand, when the demand for item is independent of the demand of any other item in inventory. They don't depend on each other. The dependent demand, when the demand for an item is dependent upon the demand for some other items in inventory. This chapter will be addressing independent demand only. We'll talk about dependent demand if we have a chance in other chapters. Uh, there are three costs that can be identified in inventory: the holding cost, the ordering cost, and the setup cost. The holding cost is the cost of holding or carrying inventory over time. When you put it on the shelf, if you have it on the shelf there for a long time, that's a holding cost. Then we have to calculate that cost that will be associated with putting the item on the shelf. Ordering cost, the cost of placing an order and receiving goods. When you order, you have a cost for ordering. You are paying for people to order, to find the item and purchase it and bring it to the inventory. So that is ordering cost. Setup cost is the cost to prepare a machine or a process for manufacturing an order, which may highly be correlated with the setup time for that machine. The holding cost can be determined through identifying the different areas affecting that cost, such as housing cost, which includes building rent or depreciation, operating cost, taxes, and insurance. That could vary from 3 to 10% of the inventory value. Material handling cost, which include equipment lease or depreciation, power and operation cost, that varies between 1 and 3.5% of the inventory value. And then we have labor cost, which includes receiving, warehousing, and security, that varies between 3 and 5% of the inventory value. The investment costs, which include borrowing costs, taxes, and insurance on inventory, that varies between 6 and 24%. The costs caused by pilferage or small like theft, space, and obsolescence, that varies between 2 and 5%. And the overall carrying costs for example, in the slide in this slide is 26 of inventory value. So the overall carrying cost, if you add all of them, the housing cost, the material handling cost, labor cost, investment cost, and cost of obsolescence and cost of space and little theft, will be altogether 26% of the inventory value. Taking the lowest possible percentage, you can see that holding costs will not be less than 15%. Even if you assume that most of them will be zero, but at least one will be there, and that will be the least, which is 15%. And you cannot assume zero because, as we said, with the range that we have, if you go back to the slide, the lowest here is 3, the lowest here is 1, the lowest here is 3%, the lowest here is 6, and the lowest here is 2%. So basically, even with the lowest, if I take the lowest, still it will be 15%. That's the lowest for each one of them. So that's a total 15%, and again, with all these values and the 15%, it's still the holding cost is there, and it's a big percentage of the inventory. So we need to minimize that holding cost. Actually, for some high-tech and fashion items, holding costs might be even greater than 40%. Holding costs vary considerably depending on the business location and interest rates. Based on the previous discussion, the company would like to keep holding costs down. Always they would like to keep their holding cost as minimum or as lower as possible. One of the methods that can be used to control inventory levels is the ability to determine when and how much to order. There are three models that are used to determine the quantity and the time of an order. The first model is called the Basic Economic Order Quantity, or EOQ model. The second is called the Production Order Quantity model, and the third one is the Quantity Discount model. The Basic Economic Order Quantity model assumes the following: the demand is known, constant and independent. Lead time is known and constant. Receipt of inventory is instantaneous and complete, which means that once I order, I will receive it, and it will be a complete order, no missing items, no broken items, no problems. Quantity discounts are not possible. It will be fixed. Only variable costs are setup or ordering and holding. Stockouts can be completely avoided. With the assumptions mentioned, inventory usage over time will follow the graph shown in this slide, where Q represents the amount that is ordered. The graph shows the maximum inventory level and the maximum when it gets to zero. The average inventory on hand will equal Q maximum divided by 2, and we can set the Q over 2 as a reordering point, which will be discussed in details at a later point in this chapter. The objective of most inventory models, any model that I use, is to minimize total cost. And this is what we said. We have holding cost, we have the setup cost, and we need to minimize the overall cost that will be associated with those items. And that is mostly the most important thing, is to minimize the cost of these items. So minimizing the sum of the setup and holding cost will minimize the total cost. From the graph, you can see that the optimal order quantity that will minimize the total cost is Q star or asterisk. As the quantity ordered increases, the setup cost decreases, but the holding cost will increase. A reduction in either cost reduces the total cost. So we need to find the point where total cost is the minimum. As depicted in the graph, that point can be reached when ordering cost and carrying cost are equal. If you see this point, this is the intersection. That means at this point, the holding cost and the setup cost will be equal. And this is where the minimum or the optimal order quantity. To find that point, we need to develop a formula for the setup or ordering cost, develop a formula for the holding cost, and then equate the two formulas to solve the equation for the optimal order quantity. So if Q is the number of units per order, Q star is the optimal number of units per order, and D is the annual demand in units for the inventory item. S is the setup or ordering cost for each order. H is the holding or carrying cost per unit per year. Then the annual setup cost is equal to number of orders placed per year multiplied by the setup or order cost per order. But number of orders placed per year will equal the annual demand divided by the number of units in each order. And according to that, then the annual setup cost will equal to D over Q multiplied by S. It's D over Q multiplied by S. And again, D is the annual demand, and Q is the number of units per order. So the annual holding cost will equal the average inventory level multiplied by the holding cost per unit per year. Based on that, the average inventory level is Q over 2, and that's what we saw from the graph. Multiplying that by the holding cost will give us the annual holding cost, which will equal Q over 2 multiplied by H, where H is the holding cost per unit per year. Since we have now the annual setup cost and the annual holding cost, we can equate both of these formulas as shown in this slide, and then cross multiply with some algebra. We will get that 2ds will equal to q squared h, dividing by the two sides by h. We will get that q squared is equal to 2ds divided by h, or q is equal to the square root of both, the square root of 2ds divided by h, and that is what we call q optimal, or the optimal quantity, q star to q asterisk, or optimal quantity. Um, a company would like to determine or to produce or to reduce the inventory cost by determining the optimal number to obtain per order. Knowing that the annual demand is 1000 units, the setup or ordering cost is $10 per order, and the holding cost is 50 cents per unit per order per year. Using the formula, Q star will equal the square root of 2ds divided by h, and substituting the values of d, s, and h. Again, d is 1000, s is 10, and h is 0.50. So substituting all these values will give us the square root of 40,000, which is 200 units. So the optimal quantity to order, and reduce the cost, overall cost, is 200 units. To determine the expected number of orders, n, we divide the demand by the optimal quantity, that is 1000 divided by 200, which means that I need to make 5 orders per year. So to get the 1000 per year, we divide the 1000 divided by 200, and that's the optimal per order, and we will have 5 orders per year. To calculate the expected time between orders, when I order something, that does not mean it will come immediately. So I need to calculate how much time would it take between orders, which is basically asking when to order. We divide number of working days per year by the expected number of orders. That is 250 divided by 5 orders, which will equal to 50 days between orders. And again, you have to understand that 250 number of days is calculated based on the number of weeks multiplied by number of days per week. Knowing all the information to calculate the total cost, the total annual cost will equal setup cost plus holding cost, which will equal $100, and that does not include the cost of goods. So if you look at the calculation and how we added the setup cost plus the holding cost and got at the end $100, you can see that we did not include the cost of goods. When including actual cost of material, the total annual cost will equal setup cost plus holding cost plus the product cost, where the product cost will equal the cost of the material multiplied by the demand. The basic model, basic economic model, is robust, which means that it will work even if all parameters and assumptions are not met. Even if there was a slight change, it will still work. The total cost curve is relatively flat in the area of the EOQ, which will give a range of variability for that model to work. For example, if we change the demand from 1000 to 1500 units, using the old optimum quantity, the total cost will equal $125. Using the new optimal quantity, which will equal 244.9 units. Going through the calculations that we did in the previous example, the total cost will equal 122.122.47. That is only 2% less than the total cost of 125 when the order quantity was 200, although the variability of the demand was an increase of 50%, the change in the total cost was only 2%. So if you look at the change, and you can see from the different quantity from 200 to 244, but still the change in the total cost was from 125 to 122, and that's only 2%. For that, the economic order quantity is considered to be a robust model because even with that variation, we did not see lots of variability in the overall cost or the total cost of inventory. With this, we will end, and we will continue later on with the other models, demand models for inventory. So we'll talk about that later on. But for now, that will be all. If you have any questions, please let me know. I will be more than glad to assist you with that. Thank you and have a great day.